Interchanging sum is really helpful in such cases. So basically, let's see like what the case is and how is it helpful. So basically, in this sum, the inner sum is in the world of n. So you can take x to the power m outside. Yeah. So m equals to 1 to infinity x to the power n, and the sum from n equals to 1 to m as n, and then this over here means that it is skew harmonic number. If you don't know what skew harmonic number, let me just give a brief intro. So this is harmonic number and this is skew harmonic number. This implies that this denotes 1 minus 1 by 2 plus 1 by 3 up to n. So basically in second term there's minus, so in nth term uh, I should write plus 1 by n. Yeah. Now in the harmonic number is just the sum 1 plus 1 by 2 plus 1 by 3 up to 1 by n. Okay. Now if you know this too, now if you want to like sum, like here we have a partial sum of skew harmonic number up to m, and we don't really have such expressions, or even if we have, those are complicated stuffs. So this sum is not really easy to carry out. Yeah. So that's why in this case it's beneficial for us to interchange the sum. Yeah, first sum in the world of m and then in the world of n, because if it's in the world of m first, this one is easy to evaluate. Yeah. So that's why we will try interchanging the sum in this case. But here the first one is in from 1 to infinity, second from 1 to m. Yeah. So basically, if we had such sums, let's say from m equals to 1 to some constant c1, from n equals to 1 to some constant c2, and then am bn, it would have been easier if it converges absolutely. Then we could have just interchanged easily. Yeah. But over here in this sum, what happens is this first sum is dependent on the second sum. So that's why like we cannot really interchange it as easily as over here. Yeah. So basically we have a formula which I will also prove and then use to solve this problem. So basically if you have sum from m equals to 1 to infinity, and then sum from n equals to 1 to m of a of m b of n, then this is equal to sum from n equals to 1 to infinity, sum from m equals to n to infinity, am bn. So we have this identity. This identity will be helpful in solving this problem. So if you want a quick proof of this thing, what you can do is you can take the first expression, and that thing is, so over here we can take a of m outside, and this is just b1 plus b2 up to bm. Yeah. And now over here, okay, so when m is 1 we have a1, and this sum is going up to m, so just up to b1 for now, plus now when m is 2 we have a2 b1 plus a2 b2. Yeah, we basically have b1 plus b2. And when this is 3, we have a3 b1 plus a3 b2 plus a3 b3. Yeah. And same for f4 as well. Yeah, a4 b1 plus a4 b2 plus a4 b3 plus a4 b4, and that ends. Now in a similar fashion, like it goes down. Yeah, and it goes over here as well, it goes down. Okay, now if I want to write this sum in a different way, so for example, if I let's say take out b1 common, now I have a1 plus a2 going up to infinity. Yeah. And then if I take b2, I have a2 plus a3 going up to infinity. Initially we had am common, now I am taking bm common to interchange the sum. Now if I take b3 common, we have a3 plus a4, and so going up to infinity. and so on is the case. If I have b4, a4 plus a5 going up to infinity. Yeah. Now you can write this as okay. So basically, n going from 1 to infinity, and for the m for a is going from, if the n is 2, it's going from 2. Yeah. So that's why I can write this as m equals to n to infinity, from n to infinity. And over here I just have, so these are bm and this is sum of am, bm sum of am. So bm can be written over here, bn, and over here this is sum of am. Yeah. So now I can take the bn out inside, because the sum is all in the world of m, and bn is a constant. So that's why I can write this as sum from n equals to 1 to infinity, sum from n equals to n to infinity, am bn. So this is a quick proof of this identity. And now let's use this thing to interchange the sum and prove this sum. Now we have sum going from m equals to 1 to infinity, sum from n equals to 1 to infinity, not infinity, up to m, x to the power m as a complement, which is skew harmonic number. Now let's interchange this. We have sum from n equals to 1 to infinity and sum from m equals to n to infinity. Now x to the power m skew harmonic number. Now this is a constant. Let's take this inside. Yeah, this is a constant for the world of m only. So let's take this over here. Now summing up x to the power m, let's assume that the modulus of x is less than 1. Let's do it for that case. In that case, our sum will be, first term is x to the power n. Yeah, first term is x to the power n, and common ratio is x. So 1 minus x. Now we can take 1 by x outside, 1 by 1 minus x. Now this is sum from n equals to 1 to infinity, and now x to the power n is there, and our hn is just sum from k equals to 1 to infinity minus 1 to the power k plus 1 by 1 by k. Yeah, isn't this? Okay, but wait, it's up to n, so not up to infinity, just up to n only. Okay, so sum from k equals to 1 to n minus 1 to the power k plus 1 by 1 by k. Now you can again use that same identity, 1 by 1 minus x. First of all, you can take x to the power n inside, yeah, so that it will be in a good format. Sum from k equals to 1 to n, here minus 1 to the power k plus 1 by k, and then we have x to the power n. Now let's interchange these two by using the formula that I told earlier. Sum from k equals to 1 to infinity, sum from n equals to k to infinity. Now this is minus 1 to the power k plus 1 by k, x to the power n. Now minus 1 to the power k plus 1 by k is just constant for the world of n. That's why I can take this outside. 1 by 1 minus x, sum from k equals to 1 to infinity minus 1 to the power k plus 1 by k, and this is sum from n equals to k to infinity of x to the power n. So again, since our modulus of x is less than 1, we can use geometric series. The first term is x to the power k, and common ratio is x by 1 minus x. Now I can again take 1 minus x outside. That gives me 1 by 1 minus x whole square. This is sum from k equals to 1 to infinity, and this is minus 1 to the power k plus 1 x to the power k by k. Now this is a well-known result. Yeah, this is just a series for ln of 1 plus x. So you have it there, ln of 1 plus x by 1 minus x whole square. This is our answer. Now I want to give you one problem to try. Yeah, basically what I want you to do is you can also try to find the other uh, formula. Yeah, basically over here we had uh, okay, so over here when 1 minus x was taken out, we have skew symmetric skew harmonic number times x to the power n. Yeah, basically over here we got n equals to 1 to infinity skew harmonic number times x to the power n. As what did you get? We get ln of 1 plus x by 1 minus x. Yeah, now here's another problem to try for you using this identity. Basically hn times x to the power n. Try to prove that this is actually equals to minus ln of 1 minus x by 1 minus x. That's the problem for you. Okay, so hope you enjoyed the video. So basically hope you got the idea about like how to interchange in these cases. Yeah, when the first sum is dependent on the second, yeah, dependent on the second or whatever, and like how to we do when there's are constant in the upper bound, and how these are in fact helpful. Yeah, something that seems unsolvable is solvable when we interchange the sums. So basically like my intention was to let you know the importance of interchanging, and yeah, I hope you got that from this video, and I hope you also got the idea about skew harmonic numbers. Thanks for watching. Look forward to seeing in the upcoming videos too.